Our view of the cosmos is not something we are born with, it is something we build. The true story of astronomy is not just about brilliant minds, but about brilliant machines. It is the story of the tools we have created to extend our senses beyond this world. This is a journey through 25 observatories that did not merely observe, they transformed. From a circle of ancient stones to a telescope floating in the void, each one forced humanity to rewrite its place in the universe. This is not a simple list of powerful telescopes. It is the story of how specific instruments shattered specific illusions and revealed fundamental truths. By the end, you will see the entire arc of cosmic discovery, from our own backyard to the edge of time and space. How did a simple arrangement of rocks first tie human fate to the stars, and what invisible force did we only learn to sense in the last decade? The journey of discovery is never really about finding final answers. It is about building better questions. What do you think it means to truly see? Long before lenses or satellites, our first observatories were built from earth and sky. On the windswept plains of southern England, a circle of massive stones stands as a silent testament to a profound shift in human consciousness. This is Stonehenge, and to call it merely a calendar is to miss its true power. For the people who raised these sarsen blocks over 4,000 years ago, this was a monumental machine for reading the cosmos. Its architecture is a precise alignment with the heavens. At dawn on the summer solstice, the sun rises directly over the heel stone, casting a beam of light into the heart of the circle. On the winter solstice, the sun sets framed perfectly between the tallest trilithons. But it was more than the sun. Researchers believe the station stones tracked the more complex 18.6-year cycle of the moon. This was not casual stargazing, it was systematic, engineered observation. By marking these celestial turning points with such permanence, they transformed the sky from a chaotic tapestry of lights into a predictable, measurable clock. This changed everything for a society transitioning from nomadic life. Knowing when to plant, when to harvest, and when to hold ceremonies meant survival and community. Stonehenge anchored human culture directly to the cosmic order, turning abstract celestial patterns into the very rhythm of life on Earth. It was our first great step out of ignorance, a declaration that the heavens could be understood and that understanding could be built in stone. That desire to measure the sky did not stay isolated on lonely plains. It moved into the heart of the city. Centuries after Stonehenge, in the bustling Roman agora of Athens, a scholar named Andronikos of Chios built something extraordinary. Known as the Tower of the Winds or the Horologion, this octagonal marble tower was not a monument to gods or kings. It was a public utility, a machine for urban life powered entirely by celestial observation. Each of its 8 sides faces a different wind direction, carved with a beautifully sculpted figure representing that wind, from the gentle Zephyros to the fierce Boreas. At its peak, a bronze Triton figure served as a weather vane, spinning to show citizens which wind was blowing, but the tower's true genius was in its timekeeping. Its walls were lined with multiple sundials catching the sun's angle at different hours, and when the sun was not shining, a complex water clock inside, driven by a stream from the Acropolis, took over. This was a seamless integration of astronomy, meteorology, and engineering. For the first time, precise time derived from the sun's motion was not just for priests or astronomers, it was for merchants scheduling deliveries, for citizens attending assemblies, for the entire rhythm of civic life. The shift from Stonehenge's grand celestial alignment to the Horologion's precise, public dials is profound. One marked sacred seasons for a community, the other gave the hour to a diverse city. It turned the abstract motion of the heavens into a practical, daily tool, embedding cosmic order into the very heartbeat of human society. The sky was no longer just a calendar for planting, it was the clock by which a civilization ran. Yet for all its civic genius, the horologion still measured time as it was perceived from a single city on Earth. The next great leap would require a different kind of ambition, one that sought not just to tell the hour, but to map the very fabric of the night sky with unprecedented precision. This ambition found its home in the 15th century, in the heart of the Timurid Empire, under a ruler who was also a brilliant mathematician and astronomer. His name was Ulugh Beg, and in Samarkand he built not just an observatory but a temple to measurement. The centerpiece was not a dome, but a titanic, trench-like instrument carved directly into a hillside known as the Fakhri Sextant. Imagine a giant stone arc over 150 feet long, aligned perfectly along a north-south meridian line. Its curved wall was precisely graduated, allowing astronomers to track a star's highest point in the sky with astonishing accuracy. This was an instrument built on a staggering scale to eliminate error, to pin down the positions of the stars with a certainty never before achieved. It was the engine of a state-sponsored scientific revolution where teams of scholars worked systematically, funded by the empire itself. The result was the Zij-i-Sultani, a star catalogue that detailed the positions of over 1,000 stars. Its precision was so remarkable that it rivaled the catalogues produced in Europe centuries later with the aid of telescopes. Ulugh Beg's observatory represented a pinnacle, a final, magnificent flourish of naked-eye astronomy. It preserved and advanced the knowledge of the ancients, pushing human observation to its absolute limit. But that limit had been reached. To see further, humanity needed to do more than measure the sky with bigger rulers. It needed to learn how to gather light itself. The very scale of Ulugh Beg's sextant hinted at a problem. The instrument had become as large as a building. The next transformation would not come from making instruments bigger, but from a deceptively simple invention that would make them infinitely more powerful. The limit of the naked eye had been reached, but the answer was not to build larger instruments. It was to see with new eyes entirely. In the autumn of 1609, in a small workshop in Padua, an Italian mathematician named Galileo Galilei heard whispers of a curious new device from the Netherlands, a spyglass that made distant objects appear closer. He did not invent it, but he grasped its revolutionary potential. With relentless focus, he ground his own lenses, improving the design until he had an instrument powerful enough to do something no one had ever seriously attempted. He pointed it at the night sky. In that simple, defiant act, the naval spyglass became the astronomical telescope, and the universe was forever changed. What Galileo saw was a cosmos in violent disagreement with the ancient, comfortable truths. The moon, long imagined as a perfect, smooth celestial sphere, was revealed as a world. Its surface was cragged with mountains and pitted with vast, round craters, a landscape of stark shadows and rugged terrain. It was a place, not a perfect idea. Then he turned his telescope to Jupiter and found 4 tiny, star-like points of light dancing in a line around the giant planet. Night after night, he charted their positions, realizing they were not stars at all, but moons in orbit around Jupiter. Here was a miniature solar system in motion, a direct challenge to the dogma that everything revolved around the Earth. His observations of Venus delivered perhaps the most visually elegant proof. As Venus moved in its orbit, Galileo saw it go through a complete set of phases, from a thin crescent to a full disk, just like our moon. This could only happen if Venus was orbiting the Sun, not the Earth. Even the Sun itself was not pure, its face marred by dark, moving blemishes we call sunspots, proving that celestial bodies were not immutable and perfect. Each observation was a hammer blow to the Aristotelian cosmos of crystalline spheres and an Earth-centered universe. Galileo provided not just theory but public, repeatable evidence. He turned the telescope from a novelty into the fundamental tool of discovery, the instrument that would pry open the heavens and hand humanity a universe vaster, more dynamic, and far more mysterious than anyone had dared to dream. Galileo had turned a curiosity into a weapon for discovery, but the telescope was still a personal instrument, a tool for brilliant individuals. The next great leap required something more systematic, an entire institution built around the methodical pursuit of celestial truth. That institution was born in Paris in 1667, not from the mind of a lone astronomer, but from the will of a state. King Louis XIV's finance minister, Jean-Baptiste Colbert, laid its cornerstone, creating the Paris Observatory as the world's first national scientific institution dedicated purely to fundamental research. This was a radical idea, science not as a hobby for nobles or a tool for navigation, but as a state-sponsored endeavor to master the natural world. Its very architecture reflected this new ambition, a fortress of knowledge designed with precise meridians etched into its floors, its foundations aligned to the cardinal points, transforming the entire building into a scientific instrument. The observatory's mission was twofold: to map the land and to map the heavens with equal precision. On Earth, its astronomers embarked on a grand project to remeasure France itself, correcting maps with such accuracy that the king reportedly joked he had lost more territory to his astronomers than to his enemies. In the sky, they tackled the greatest practical puzzle of the age, determining longitude at sea. By meticulously observing the moons of Jupiter as celestial clocks, they provided a method for sailors to find their east-west position, taming the oceans for empire and trade. But their vision looked even further. Under directors like Giovanni Cassini, they used observations of Mars from Paris and French Guiana to triangulate the distance to the red planet, providing the first accurate scale of the solar system. We learned that the void between planets was not just vast but staggeringly, humblingly so. The Paris Observatory established the model for all modern research, a permanent home for collaboration, funded by the public purse, devoted to long-term questions. It signaled the transition from the age of the gifted amateur with a telescope to the era of the professional using a purpose-built, state-of-the-art refractor in a dedicated dome. The cosmos was no longer just to be observed, it was to be measured, catalogued, and understood by a permanent army of the night. But even the Grand Paris Observatory had a fundamental limitation: the nature of light itself. The lenses in their long, elegant refractor tubes suffered from a flaw called chromatic aberration, where different colors of light focus at slightly different points. This created fuzzy, rainbow-hued halos around stars, a constant blurring of cosmic detail. For over a century, this was simply the price of admission for a closer look. Then, in the small university town of Dorpat, now Tartu in Estonia, a German optician named Joseph von Fraunhofer achieved what many thought was impossible. He did not just build a better telescope, he crafted a masterpiece of glass and brass that redefined perfection. Completed in 1824, the Great Refractor of Dorpat was a 9-inch aperture instrument that seemed to defy the laws of optics. Fraunhofer's genius lay in his unprecedented control over glassmaking. He formulated new types of optical glass with specific properties, then meticulously ground and polished the lenses to a shape that almost completely eliminated the color distortion that had plagued all previous refractors. The stars it revealed were not smeared points of light, but sharp, brilliant pinpricks against the deepest black. Paired with this optical marvel was an equally revolutionary mounting, a massive, clock-driven equatorial design that moved with a smooth, mechanical grace. Once an astronomer locked it onto a target, the clockwork drive would compensate for Earth's rotation, keeping the object perfectly centered in the eyepiece for hours. This stability was as transformative as the clarity. It meant an observer could now study a single star or nebula with sustained microscopic attention, noting details that would have drifted away in a stationary telescope. This combination of clarity and stability opened a new frontier, the subtle architecture of deep space. Astronomers like Friedrich Wilhelm Struve used the Dorpat refractor to meticulously chart double stars, pairs of stars bound by gravity, measuring their tiny orbits to weigh the stars themselves. It revealed nebulae not as shapeless clouds, but as objects with delicate, structured forms, hinting at cosmic processes far beyond our understanding. Fraunhofer's instrument did not discover a new planet or comet. Its legacy was more profound. It set an unshakable new standard for engineering precision, proving that with perfect materials and impeccable craftsmanship, the telescope could become a flawless window. It was the zenith of the human eye partnered with glass, a final, glorious proof that before we could capture the sky with photography, we first had to learn to see it with absolute clarity. But perfect clarity through a lens had its own physical limit. To see deeper into the cosmic dark, you needed to gather more light, and that demanded a mirror of impossible size. In the damp, remote countryside of Ireland, an earl with a passion for engineering decided to build it himself. William Parsons, the third Earl of Ross, was not a professional astronomer. He was a wealthy man with a brilliant, restless mind, and at his estate at Birr Castle in 1845, he embarked on an audacious private enterprise. He would construct the largest telescope the world had ever seen. They called it the Leviathan of Parsonstown. Its heart was a 72-inch wide mirror, but this was not glass. It was speculum metal, a brittle alloy of copper and tin that had to be cast, ground, and polished by hand. The process was fraught with peril. The first casting cracked during cooling, a devastating loss of time and material. Undeterred, Lord Ross and his team built a special rotating furnace to ensure even cooling for the next attempt. Polishing the massive, heavy disc to a perfect parabolic shape took months of relentless, painstaking labor. The finished mirror was then mounted at the bottom of a 54-foot-long wooden tube, itself slung between two massive stone walls that acted as the telescope's support. It looked less like a modern observatory and more like a siege engine pointed at the stars. Operating it was a physical ordeal. The observer stood on a precarious platform high on the wall, steering the giant tube with ropes and pulleys, braving the cold Irish night to peer into an eyepiece that brought the gathered light of the cosmos to a single point. And what a point it was! The Leviathan's true triumph came when Lord Ross turned it toward a faint smudge in the constellation Canes Venatici, known as M51. Through all previous telescopes, it was just a nebulous oval of light, but through the Leviathan's colossal eye, it resolved into something breathtaking, a distinct spiral structure, a whirlpool of starlight. He called it a spiral nebula. This was a revelation of cosmic architecture. That faint patch was not a formless cloud of gas within our own Milky Way. It was a vast, structured system, an island of stars perhaps as grand as our own. The Leviathan planted the profound seed of a new idea, that our universe might be filled with such island universes, each a separate, swirling metropolis of stars. For over 70 years, it remained the largest telescope on Earth, a monument to what sheer ambition and craftsmanship could reveal. It showed that to see the true shape of the cosmos, you sometimes had to build something that looked like it belonged in a medieval castle and point it at the sky. The Leviathan revealed the shape of galaxies, but it could not tell us what they were made of. That question required a different kind of observatory, one that treated the stars not as singular points of light, but as a vast population to be catalogued and understood. This shift happened not with a single giant telescope, but in a quiet brick building in Cambridge, Massachusetts, at the Harvard College Observatory. Here, under the direction of Edward Pickering, astronomy transformed from an observational art into a data-driven science. The engine of this revolution was a monumental project, the Henry Draper Catalogue, named for an amateur astronomer whose widow funded the work. Its goal was audaciously simple: to photograph, measure, and classify every star in the sky. Night after night, telescopes equipped with new photographic plates captured the heavens, producing not sketches or fleeting glimpses, but permanent, detailed records. These plates piled up by the thousands, each one a glass negative speckled with countless stellar images and their unique, hidden fingerprints, their spectra. The real challenge was not collecting this data, but deciphering it. To tackle this ocean of information, Pickering made a pragmatic and revolutionary decision. He hired a team of highly skilled, meticulous women, known as the Harvard Computers, to analyze the plates. For a fraction of a male astronomer's salary, these women, including pioneers like Williamina Fleming, Antonia Maury, Annie Jump Cannon, and Cecilia Payne-Gaposchkin, did the painstaking, brilliant work that would redefine our understanding of the stars. Day after day, they peered through magnifying glasses at the spectral lines on the plates, sorting stars into categories based on the elements they revealed. Annie Jump Cannon perfected the iconic OB-AFGKM spectral sequence, remembered by generations of astronomy students with the mnemonic "OB a fine girl, kiss me." This was not just sorting, it was taxonomy that revealed stellar evolution. Their work showed that a star's color and spectral class were directly linked to its temperature and stage in life. But the most profound discovery came from Cecilia Payne's analysis of this very data. Her doctoral thesis, built on the foundation of the computer's classifications, concluded something astonishing: that stars were overwhelmingly composed of hydrogen and helium. This contradicted the established wisdom of the time, but she was ultimately proven correct. The Harvard College Observatory, through its systematic cataloging and the unsung labor of its computers, did more than classify the stars. It gave us the periodic table of the cosmos, revealing that the same simple elements make up nearly everything we see in the universe. It proved that astronomy could be a science of big data, where patterns across millions of points of light reveal truths no single brilliant observer could ever find alone. Harvard's data revealed the composition of the stars, but to truly understand them, we needed to dissect their light in exquisite detail. That required an instrument of unparalleled precision, a final, magnificent monument to the age of glass. On the shores of Lake Geneva in Wisconsin, the Yerkes Observatory opened its doors in 1897, housing a breathtaking creation, the 40-inch Great Refractor. Its lens, the largest ever successfully cast and polished, was the pinnacle of a dying art. To stand beneath its 60-foot-long tube, suspended in a cathedral-like dome, was to witness the zenith of 19th-century engineering ambition. Yet Yerkes was not built as a relic, it was conceived as a bridge. Its founder, astronomer George Ellery Hale, saw it as the perfect instrument for a new science he called astrophysics, the study of the physics of the stars. The refractor's supreme clarity and stability made it an ideal platform for spectroscopy. By attaching delicate prism spectrographs to its eyepiece, astronomers could spread starlight into rainbows so detailed they looked like intricate barcodes. Each dark absorption line in that spectrum was a chemical signature, a direct message from a star's atmosphere millions of light years away. At Yerkes, this technique moved from novelty to rigorous science. Astronomers could now classify stars not just by their Harvard catalog type, but by understanding the physical conditions, the temperature, pressure, and elemental abundance that created those spectral lines. They were taking the cosmic census started at Harvard and giving it a profound new depth, learning not just what stars were made of, but how they worked. The observatory also pioneered the use of photography for systematic sky surveys, capturing wide fields of stars with the refractor's sharp optics to create permanent maps for future study. But for all its power, the Yerkes refractor was a glorious in point. Its 40-inch lens represented a practical ceiling, a point where the massive, heavy glass disc would sag under its own weight, distorting the very light it sought to collect. Hale knew this. Even as Yerkes was being celebrated, he was already dreaming of the next leap, not with lenses, but with mirrors that could be supported from behind, mirrors that could, in theory, be made infinitely large. Yerkes was the grand finale of one era and the blueprint for the next. It proved that the future of discovery lay not in perfecting the old tools, but in harnessing new ones from new places, from the clear, dark, and thin air of remote mountaintops. The clear, thin air of Mount Wilson in California offered a new frontier for astronomy's ambition. Here, George Ellery Hale's vision for giant mirrors became reality, first with a 60-inch telescope, and then, in 1917, with a tool that would redefine the cosmos itself, the 100-inch Hooker telescope. Its massive mirror, cast from tons of glass and coated in reflective silver, gathered starlight with a power that dwarfed all that came before. This was the instrument that gave Edwin Hubble the keys to the universe. Night after night, he used the Hooker's immense light-gathering power to study faint, cloudy patches called spiral nebulae. The great debate of the era was simple yet profound. Were these nebulae small, nearby clouds of gas within our own Milky Way, or were they vast, distant islands of stars? Hubble found the answer hidden in the flicker of a special kind of star within the great nebula in Andromeda. These were Cepheid variable stars, cosmic lighthouses whose intrinsic brightness was linked to the rhythm of their pulsations. By measuring how dim they appeared through the Hooker telescope, Hubble could calculate their staggering distance. The result was unequivocal. Andromeda was nearly 1 million light-years away, far beyond the outer limits of our own galaxy. In an instant, the Milky Way was dethroned from being the entire universe to being just one galaxy among countless others. Our cosmic address had expanded exponentially. But Hubble did not stop there. By measuring the light from many other galaxies, he noticed something even more astonishing. Their light was shifted toward the red end of the spectrum, and the farther away a galaxy was, the greater this redshift. The only plausible explanation was that space itself was stretching, carrying the galaxies apart from one another. The universe was not static and eternal, it was dynamic and expanding. The 100-inch Hooker telescope provided the raw visual evidence for both revelations. It moved humanity from a cozy, single-galaxy neighborhood to an unimaginably vast and actively evolving cosmos, setting the stage for every major cosmological discovery that would follow. The question was no longer what the universe was made of, but where it all came from and where it was going. The expansion of the universe was now a fact, but its details were still hidden in the faintest glimmers at the edge of perception. To map this new frontier, astronomy needed a new titan, an instrument of such overwhelming power it could become the definitive eye on the cosmos for a generation. That titan was the 200-inch Hale telescope at Palomar Observatory, and its creation was an epic struggle of engineering against the limits of human ingenuity. Its mirror, the heart of the beast, was a disk of Pyrex glass over 17 feet across, weighing over 14 tons. Casting it without cracks or bubbles was a nightmare of thermodynamics, requiring a special oven and years of slow, controlled cooling. Grinding its surface to a perfect parabolic curve took over a decade of meticulous work, a labor of such precision that work was halted during the day because the heat from the workers' bodies could warp the glass. The finished mirror, coated in a thin layer of reflective aluminum, was mounted in a dome so large it had its own weather system, where astronomers worked from cages high above the mirror's surface. When it saw first light in 1949, it was not just a bigger telescope, it was a national project, a symbol of American scientific might in the post-war era. For decades, it was the preeminent instrument on Earth, the ultimate workhorse of discovery. Its immense light-gathering power turned faint smudges on photographic plates into detailed portraits of distant galaxies, allowing astronomers like Alan Sandage to painstakingly measure the rate of the universe's expansion, refining the Hubble constant. But its most startling finds were objects that defied comprehension: quasi-stellar radio sources, or quasars. Through the Hale telescope, these pinpoints of light were revealed to be the most luminous objects in the universe, shining with the power of 1,000 galaxies from distances so vast their light had been traveling for billions of years. They were the furious hearts of young galaxies, powered by supermassive black holes. Palomar did not just confirm the cosmological revolution from Mount Wilson. It exploded it into a rich, detailed map of deep time and large-scale structure. It showed a cosmos filled with violent, energetic phenomena, and gave us the first reliable chart of the expanding universe's history. The Hale telescope was the final, glorious monument to the era of human observers peering through an eyepiece, a steel and glass sentinel that held the deep sky in its gaze and handed us a universe more dynamic and strange than Hubble himself could have imagined. The Titans of Palomar saw the cosmos with breathtaking clarity, but they were still blind. They saw only the narrow slice of reality our eyes can perceive, the rainbow of visible light. The universe, however, is an orchestra playing across the entire electromagnetic spectrum, from the high-pitched gamma rays to the low, rumbling hum of radio waves. To hear that symphony, we needed a new kind of ear. In the quiet English countryside of Cheshire, a colossal, skeletal bowl of steel rose from the ground, not to gather light but to catch whispers from the void. This was the Lovell telescope at Jodrell Bank, and when it was completed in 1957, it did not just look at the stars, it listened to them. This giant, steerable radio dish was an instrument of audacious scale and purpose. Its 250-foot wide parabolic surface was a net, designed to catch the faintest radio waves streaming from space, focusing them onto a receiver high above its center. Its completion was perfectly, dramatically timed. Just weeks after it became operational, the Soviet Union launched Sputnik, the first artificial satellite. While the world listened to its beeping transmission on the radio, Jodrell Bank did something more. It tracked the rocket body that carried it into orbit. For the first time, humanity had an instrument powerful enough to watch our own technology move through the cosmos, a capability that would define the early space race and usher in the era of satellite tracking and deep space communication. But its true destiny was far beyond Earth. The Lovell telescope opened a window onto a universe utterly invisible to optical telescopes. It revealed a cosmos crackling with radio energy. It was instrumental in pinpointing the locations of the mysterious quasars first glimpsed at Palomar, confirming they were indeed staggeringly distant and energetic. Then, in 1967, it played a key role in one of the most startling discoveries of the century. A graduate student named Jocelyn Bell Burnell, working with a smaller array at Cambridge, detected a strange, perfectly regular radio pulse from deep space, ticking with the precision of an atomic clock. The source was dubbed a pulsar. The Lovell telescope was quickly turned toward it, confirming the signal and helping to establish that these were not alien beacons, but the spinning, lighthouse-like beams from ultra-dense, city-sized corpses of stars called neutron stars. This was a new, extreme state of matter predicted by theory but never before observed. Perhaps most profoundly, radio astronomy revealed that the cold, dark voids between stars were not empty. The Lovell telescope and others like it detected the spectral signatures of complex molecules floating in interstellar space, from simple water to organic compounds like formaldehyde. This showed that the raw ingredients for life were not unique to planets, but were scattered abundantly across the galaxy, woven into the fabric of nebulae. Jodrell Bank transformed astronomy from a purely optical science into a multi-wavelength discipline. It taught us that to understand the cosmos, we must listen as well as look, hearing the stories told by colliding galaxies, dying stars, and the faint, cold chemistry of creation itself. The silent movie of the heavens was over, now it had a soundtrack. The radio universe was now a symphony of whispers and pulses, but to hear its faintest secrets required an instrument of almost unimaginable scale. In the lush-cast hills of Puerto Rico, a natural bowl in the earth became the site for an engineering marvel that would dominate radio astronomy for over half a century. The Arecibo Observatory was not a steerable dish, but a fixed 305-meter-wide spherical reflector, a colossal bowl of perforated aluminum panels cradled by the jungle. Its scale was its power, a net so vast it could catch the faintest radio signals from across the galaxy. To aim this giant, the receiver platform was suspended 500 feet above the dish by a complex web of cables strung from 3 towering concrete supports. Engineers would steer the platform with millimeter precision, moving the focus across the sky and listening to the universe. Arecibo's great strength was its dual identity. In its active mode, it was a powerful planetary radar. It would beam a focused radio signal toward planets, moons, and asteroids, then catch the faint echo that bounced back. This allowed scientists to map the surface of Venus through its perpetual, opaque clouds, revealing volcanoes and mountains. It measured the rotation of Mercury, finding it was not tidally locked to the Sun as once thought. It even imaged near-Earth asteroids, assessing their shapes and orbits. In its passive listening mode, Arecibo was a sensitive ear for cosmic phenomena. Its immense collecting area made it a premier discoverer of pulsars, those spinning neutron stars. In 1974, it found a pulsar of profound importance, PSRB 1913+16. This was not a lone star, but a binary pulsar orbiting another dense neutron star. The discovery provided a near-perfect natural laboratory for testing Einstein's theory of general relativity. As the 2 stars spiraled inward, they lost energy in the form of gravitational waves, their orbital decay matching Einstein's predictions with stunning precision. This indirect confirmation of gravitational waves earned its discoverers the Nobel Prize and cemented Arecibo's role in fundamental physics. For decades, it was an icon of science, featured in films and representing humanity's search for cosmic intelligence through projects like SETI. Its very immensity, however, became its vulnerability. The massive, aging support structure could not be maintained indefinitely, and in December 2020, the receiver platform catastrophically collapsed, tearing a gash through the legendary dish. The loss was a profound moment for the scientific community and for Puerto Rico, silencing a unique voice in the cosmic conversation. Yet its legacy was clear. It had proven that to hear the universe's quietest songs and shout back into the darkness, you sometimes had to build an instrument that became part of the Earth itself. The era of the solitary giant was ending, but its final lesson was that the next great leap would come not from one eye, but from many working as one. The collapse of Arecibo was a loss, but its final lesson was already being learned across the desert plains of New Mexico. Here, a different philosophy had taken root, one that traded the vulnerability of a single giant for the distributed power of a team. The Very Large Array is not one telescope, but a constellation of 27 identical radio dishes, each 82 feet across, moving in silent choreography along a vast Y-shaped network of railroad tracks. This is the instrument that taught the world what the radio universe truly looks like. Its power comes from a technique called interferometry. Instead of gathering light in one spot, each dish captures the same faint radio signal from space. By combining the signals from all 27 antennas and using the precise timing differences as the Earth rotates, astronomers can synthesize a single, virtual telescope with a resolution equal to a dish as wide as the entire array is across, over 22 miles. It is a masterpiece of computational imaging, turning a scattered chorus of whispers into a single, crystal-clear picture. Before the VLA, radio astronomy produced blobs and graphs, data points for specialists. The VLA changed that. It produced portraits. It revealed the colossal, magnetized jets of superheated plasma screaming from the hearts of active galaxies, stretching for thousands of light years. It peered into the dusty cradles of star formation, mapping the swirling disks of gas and dust where planetary systems are born, seeing through the cosmic dust that blinds optical telescopes. Perhaps most subtly, it charted the invisible architecture of magnetic fields that thread through galaxies and supernova remnants, forces that shape cosmic evolution yet leave no trace in visible light. The VLA made the invisible not just detectable, but vividly, beautifully visual. It gave the public iconic images of a universe painted in radio waves, proving that some of the cosmos's most dramatic stories are told not in light, but in the long, silent waves that our eyes can never see. The era of the solitary giant was over, replaced by the coordinated symphony of many, a principle that would soon be applied on a truly global, and then interstellar, scale. But the quest for greater resolution demanded a more audacious leap than even the VLA could provide. To see the cosmos in its finest detail, we needed to build an eye as wide as the Earth itself. This was the vision of the Very Long Baseline Array, or VLBA, a network of 10 identical radio telescopes stretching from Hawaii to the Virgin Islands. Separated by thousands of miles, they operate not as a physical instrument, but as a single, continent-sized virtual telescope. Their secret is not a physical connection, but the precise atomic clocks installed at each site. Each dish independently records the faint radio whispers from a distant quasar or a stellar explosion, time-stamping every nanosecond of data with absolute precision. Later, those mountains of recorded data are brought together and correlated by a supercomputer, aligning the signals as if all 10 dishes were connected by a perfect, rigid structure. The resulting resolution is almost beyond comprehension, allowing astronomers to see details equivalent to spotting a baseball on the surface of the moon. This staggering power has been turned on the most extreme environments in the universe. The VLBA has peered into the very hearts of active galaxies, mapping the swirling disks of material just outside the event horizons of supermassive black holes. It has tracked the motions of stars orbiting our galaxy's own central black hole, providing the most precise measurements of its immense gravity. It has even watched the aftermath of stellar cataclysms in real time, monitoring the expanding shockwaves from supernova as they tear through space. By stitching together a continent into a single instrument, the VLBA achieved the ultimate goal of ground-based astronomy. It eliminated the final barrier of our atmosphere's size. It gave us a telescope with a lens as wide as our planet, proving that our greatest tool for discovery is not just engineering, but our ability to connect and synchronize our efforts across vast distances. This principle of distributed observation would soon be taken to its logical extreme, not by linking dishes across a continent, but by launching them beyond the atmosphere entirely, to a quiet point of perfect balance between our world and the sun. Earthbound telescopes had finally achieved a perfect view, but only by escaping the planet entirely could we truly open our eyes. Launched in 1990, the Hubble Space Telescope was not merely an instrument. It was an observatory in exile, a 2.4-meter mirror, and a suite of cameras placed in the ultimate high ground, 400 kilometers above the distorting shimmer of Earth's atmosphere. Its early days were a public drama of heartbreaking failure, when a flaw in its primary mirror meant it saw the universe as a blur. Yet this very public struggle set the stage for its greatest triumph, a daring space shuttle repair mission that turned a technological embarrassment into a symbol of human ingenuity. Once fixed, Hubble delivered on its promise with breathtaking clarity. Freed from atmospheric turbulence, it could stare at a single patch of seemingly empty sky for days, gathering the faintest glimmers of light. The result was the Hubble Deep Field, an image that became an icon of cosmic perspective. By pointing at a dark speck of space no bigger than a grain of sand held at arm's length, Hubble revealed a universe crammed with thousands of galaxies, each a swirl of stars and dust, stretching back to the very dawn of cosmic time. This was not just a pretty picture, it was a core sample of the cosmos, proving that galaxies were abundant even in the early universe. Hubble's crystal vision also brought precision to our biggest questions. By observing distant supernova and Cepheid variable stars with unprecedented accuracy, it helped pin down the rate of the universe's expansion, leading to the startling discovery that this expansion is accelerating, driven by a mysterious force we call dark energy. It turned exoplanets from theoretical guesses into objects of study, directly imaging a few and analyzing the atmospheres of others by watching starlight filter through their skies. But perhaps Hubble's most profound transformation was cultural. Its images, processed into glorious full-color vistas of nebulae and galactic collisions, were not locked in scientific journals. They were released to the world, becoming desktop backgrounds, posters, and portals to wonder for millions. Hubble made the cosmos visually accessible, turning abstract astrophysics into a shared gallery of sublime beauty. It became humanity's shared eye in the sky, a reminder that the greatest discoveries are those we can all see for ourselves. Hubble showed us a universe of breathtaking beauty and profound structure, but it was still only seeing the calm, steady glow of stars and galaxies. To witness the cosmos in its most violent, explosive moments, we needed an observatory that could see the universe's sudden, terrifying flashes of pure energy. The Compton Gamma Ray Observatory, launched in 1991, was built for that singular purpose. It was an instrument designed not for patient gazing, but for catching cosmic lightning bolts. Gamma rays are the highest energy form of light, photons carrying millions of times more energy than visible light. They are produced only in the most extreme events in nature, the crushing gravity near black holes, the collisions of neutron stars, the titanic explosions of supernova. For decades, these gamma rays were a mystery, blocked entirely by Earth's protective atmosphere. Compton changed that. Orbiting high above our planet, its 4 specialized instruments acted as a panoramic sentinel, constantly scanning the entire sky for these brief, powerful flashes. Its most transformative discovery centered on the puzzle of gamma-ray bursts. Since the late 1960s, military satellites had been detecting these unpredictable, brilliant flashes of gamma rays coming from random directions in space. For over 20 years, their origin was one of astronomy's greatest enigmas. Were they relatively minor fireworks within our own Milky Way galaxy, or were they something vastly more distant and powerful? Compton's precise mapping capability provided the definitive answer. It showed that these bursts were distributed evenly across the entire sky, with no concentration along the plane of our galaxy. This simple, crucial distribution pattern was the telltale signature of a cosmological origin. Gamma-ray bursts were not local events. They were cataclysms happening in galaxies billions of light-years away. To appear so bright from such unimaginable distances meant they were, for a few fleeting seconds, the most luminous events in the entire universe since the Big Bang itself. Compton revealed a hidden cosmos of staggering violence, a realm where stars die not with a whimper, but in hyper-energetic blasts that can outshine a galaxy of 100 billion suns. It proved that the serene star fields we see are just the visible surface of a universe constantly torn by invisible, high-energy storms, rewriting our understanding of stellar death and the birth of black holes in a single, brilliant flash of data. Compton revealed a universe of invisible explosions, but that high-energy violence was only half the story. The true aftermath of these cosmic cataclysms, the lingering heat and fury, required a different kind of vision. Launched in 1999, the Chandra X-ray Observatory was designed to see the universe not in flashes of light, but in the steady, searing glow of X-rays. This is the signature of matter heated to millions of degrees, a realm where gas is so energetic it strips electrons from atoms, creating a superheated plasma that shines in this punishing light. Chandra's supreme power was not just its sensitivity, but its exquisite resolution, its ability to take this X-ray light and sculpt it into razor-sharp images. It gave us a thermal map of the cosmos, revealing a universe far hotter and more violent than we ever suspected. Where optical telescopes see the graceful spiral arms of a galaxy, Chandra sees the colossal, fountain-like jets of superheated plasma erupting from its core, powered by a voracious supermassive black hole. It peers into the expanding shells of supernova remnants, like the Crab Nebula, and sees not just the beautiful filaments of gas, but the relentless, high-energy particle wind from the spinning neutron star at its heart, a cosmic engine driving the entire structure. Perhaps its most profound contribution was to the ecology of galaxy clusters, the largest structures in the universe held together by gravity. Optical images show these clusters as dense gatherings of thousands of galaxies. But Chandra's X-ray vision revealed the true dominant component, vast, diffuse clouds of gas so hot they glow only in X-rays. This intergalactic plasma, at tens of millions of degrees, contains more ordinary matter than all the stars in all the cluster's galaxies combined. By mapping the distribution and temperature of this hot gas, Chandra provided critical evidence for the existence of dark matter. The gas is so hot it should have dissipated long ago unless it was held in place by the immense gravitational grip of an unseen mass, a dark matter halo far larger than the visible cluster itself. Chandra transformed our understanding of stellar death, showing the intricate mechanics of explosions and their remnants. It revealed how black holes feed, heating, and redistributing matter on a galactic scale. And by weighing the hot gas in galaxy clusters, it gave us one of the clearest methods for measuring the invisible scaffolding of dark matter that shapes the cosmos. It showed us that the universe's most energetic processes are not just destructive, they are the architects of its largest scale structure, a searing blueprint written in X-ray light. Chandra showed us a universe forged in searing heat, but to find the building blocks of stars and planets, we had to learn to see the cold. The Spitzer Space Telescope, launched in 2003, was our eye on the cool cosmos. Its mission was to observe the universe in infrared light, the subtle warmth emitted by objects too cold to shine in visible light, from distant galaxies to tiny dust grains floating between the stars. To do this, Spitzer had to become colder than the space around it. It carried a tank of liquid helium, cooling its most sensitive instruments to just a few degrees above absolute zero. This cryogenic chill was essential because to detect the faint infrared glow from cosmic dust clouds, the telescope itself could not radiate any heat of its own. It was a delicate instrument of ice staring into the frozen dark, and what it revealed was a hidden universe of creation, where optical telescopes see only opaque, dark clouds blotting out the stars. Spitzer's infrared vision peered straight through. It unveiled stellar nurseries in stunning detail, vast swirling cauldrons of dust and gas where newborn stars, still wrapped in their dusty cocoons, glowed with infant warmth. It mapped the structure of our own Milky Way's crowded, dusty core, seeing through the veil to confirm the presence of a supermassive black hole. Perhaps most astonishingly, Spitzer turned its cold gaze on planets orbiting other stars. By observing the slight dip in a star's infrared light as an exoplanet passed behind it, astronomers could subtract the star's glare and analyze the faint infrared signature of the planet's own atmosphere. For the first time, we could detect molecules like water vapor, methane, and carbon dioxide in the skies of distant worlds, taking the first chemical census of alien atmospheres. Spitzer transformed dust from an annoying curtain into the main character of cosmic construction. It showed us that the cold, dark stuff between the stars is not empty, it is the raw material. Those frigid dust grains are the bricks and mortar of solar systems, the reservoirs of water and organic molecules that, under the right conditions, can become the ingredients for planets and perhaps even life. It completed a fundamental picture that the universe is shaped not only by violent explosions and searing heat, but by the slow, cold accumulation of dust in the dark. Spitzer's cold gaze revealed the dusty cradles of creation, but to understand the architecture of the cosmos itself, we needed a map on an unimaginable scale. This was not a task for a single telescope, but for an industrial process of observation. At Apache Point Observatory in New Mexico, the Sloan Digital Sky Survey began not as a traditional observatory, but as a factory for data. Its modest 2.5-meter telescope was not designed for deep, poetic stares at singular objects. Instead, it was a meticulously automated machine, a cosmic scanner. Night after night, it would methodically sweep across the sky, its work guided not by human curiosity, but by a pre-programmed survey plan. Its true genius was in its camera, a mosaic of 30 charge-coupled devices, and a system that fed light from hundreds of objects simultaneously into a bank of spectrographs via fiber optic cables. This was astronomy as a production line, its goal audacious, to create a three-dimensional digital map of the universe. Over years, it imaged and catalogued hundreds of millions of celestial objects across more than a quarter of the entire sky. But the SDSS did not just take pictures, it took fingerprints. For millions of the brightest galaxies and quasars, it captured their spectra, allowing astronomers to calculate their distances. This transformed a beautiful two-dimensional star chart into a three-dimensional atlas, placing every galaxy at its precise location in the vastness of space. The resulting map was the survey's true legacy, a public database so colossal it became the foundation for thousands of astronomical papers used by researchers across the globe. This democratization of data transformed the field. A graduate student in Brazil or a theorist in Japan could mine the same cosmic dataset as the team at Apache Point, turning astronomy into a true big data science. And what that data revealed was the hidden skeleton of the cosmos. When you plot the positions of millions of galaxies in 3 dimensions, a breathtaking pattern emerges. They are not scattered randomly. Instead, they form a cosmic web, a vast architecture of dense clusters, long, delicate filaments, and enormous empty voids. Galaxies line these filaments like pearls on a string, drawn together by gravity over billions of years. The survey's most stunning find was a titanic structure within this web, the Sloan Great Wall, a filament of galaxies over 1.4 billion light-years long, one of the largest known structures in the observable universe. This was the large-scale structure of the universe made visible, the direct imprint of the Big Bang's faintest whispers amplified by gravity across cosmic time. The SDSS also revolutionized our census of the sky's most energetic objects, discovering new, exotic classes of quasars and mapping the distribution of stars within our own galaxy in unprecedented detail. It proved that the next great discoveries would not always come from looking deeper at a single point, but from looking everywhere systematically and then asking the data to tell us its story. The universe's grand design was no longer a theory, it was a map you could download and explore on your own computer. That cosmic web of galaxies, mapped by the Sloan Survey, is the grand structure of the universe, but it is built upon a foundation of invisible forces. For a century, one of those forces had been a ghost in the equations, a prediction made by Einstein that seemed almost too subtle to ever confirm. he theorized that cataclysmic events in the cosmos, like the collision of black holes, would not just release light, they would shake the very fabric of spacetime, sending out ripples called gravitational waves. These waves would stretch and squeeze space itself as they passed, but the effect would be unimaginably tiny, a distortion smaller than the width of a proton over a distance of 4 kilometers. Detecting such a whisper seemed impossible. To listen for it, we built not a telescope, but the most precise ruler ever conceived. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is a machine of almost absurd sensitivity. At 2 sites in the United States, in Washington and Louisiana, identical L-shaped structures were built, each arm stretching 4 kilometers into the distance. Inside those long vacuum tubes, a laser beam is split and sent racing down each arm, bouncing off mirrors suspended at the ends, then recombined. In perfect calm, the light waves cancel each other out. But if a gravitational wave passes through Earth, it will momentarily stretch one arm and squeeze the other, changing the distance the laser light travels by an infinitesimal amount. This minuscule change makes the light waves shift, creating a flicker of light in the detector. Isolating this signal from the constant background noise of our planet, from distant trucks to tiny earthquakes, is a monumental feat of engineering and isolation. For decades, LIGO listened in silence, an instrument waiting for a universe to speak. Then, on September 14, 2015, the cosmos shouted. A signal lasting just 0.2 of a second swept through both detectors. It was a distinctive chirp, a rising frequency that matched exactly what physicists had calculated for the final, spiraling dance of 2 massive black holes, over 1.3 billion light-years away, merging into one. This was not an observation of light or X-rays or radio waves. It was a direct feel of spacetime itself vibrating. The detection was a triumph that confirmed Einstein's final major prediction, but more importantly, it gave humanity an entirely new sense with which to explore the cosmos. We could now hear events that were completely dark to traditional astronomy. This new sense found its full power in August 2017, when LIGO detected the ripples from a different kind of collision, the merger of 2 neutron stars. Crucially, just seconds later, space-based gamma-ray telescopes saw a flash from the same region of sky. For the first time, we had both the gravitational wave soundtrack and the electromagnetic light show of a single cosmic event. This multi-messenger astronomy allowed scientists to pinpoint the galaxy where it happened and train every available telescope on it. They witnessed the aftermath in visible light, ultraviolet, X-ray, and radio, confirming that these collisions forge heavy elements like gold and platinum, scattering them across the cosmos. We learned that the gold in a wedding ring was likely forged in the violent merger of dead stars, heard and seen in unison. LIGO did not just open a new window, it connected that window to every other one we had, turning a silent movie into a symphony with a profound new instrument. LIGO gave us ears for the symphony of spacetime, but to see the blinding flash of those same cosmic collisions, we needed a different kind of sentinel. Orbiting silently above Earth since 2008, the Fermi Gamma-Ray Space Telescope is a patient watchman, its wide field of view constantly scanning the entire sky every 3 hours for the highest energy light in the universe. Where its predecessor, Compton, proved gamma-ray bursts were cosmological, Fermi monitors this dynamic, explosive sky in real time, acting as a rapid alert system for the entire astronomical community. Its most startling discovery was that the gamma-ray universe is not just about cataclysmic endings, but also about precise cosmic clocks. Fermi found hundreds of pulsars that beam not just in radio waves, but directly in powerful gamma rays. These are not the gentle radio lighthouses we knew. They are furious particle accelerators, their beams slicing through space with energies millions of times greater than visible light, revealing the extreme physics at the surface of these spinning stellar corpses. Beyond these pinpoint sources, Fermi performed a feat of subtlety, mapping the faint, diffuse glow that permeates our entire galaxy. This is the interstellar gamma-ray background, a soft light produced when cosmic rays, particles accelerated to nearly the speed of light, collide with the thin gas and dust between the stars. For the first time, we had a full sky map of the Milky Way's most energetic particle traffic, tracing the pathways of these invisible cosmic rays that constantly rain down on our planet. But Fermi's most critical role is as a universal alarm bell. When two neutron stars spiral together in a merger heard by LIGO, the collision also unleashes a blinding, short gamma-ray burst. Fermi's gamma-ray burst monitor is often the first instrument to detect this flash, instantly calculating its rough position and broadcasting coordinates to observatories worldwide within seconds. This rapid alert triggers a global scramble, turning every telescope on Earth and in space toward that patch of sky to capture the afterglow in every wavelength. Fermi does not work in isolation. It is the spark that ignites a global campaign of observation. By catching the initial, fleeting flash of the universe's most violent events, it orchestrates a chorus of instruments, from radio dishes to X-ray observatories, to witness the aftermath. It transformed gamma-ray bursts from mysterious detections into detailed, multi-messenger events we can dissect from their first explosive instant to their fading echo, proving that the most complete understanding of the cosmos comes from listening, watching, and feeling its stories unfold all at once. While Fermi monitors the universe's most violent explosions, another observatory quietly studies its most delicate beginnings. High on the Chandra Plateau in the Chilean Atacama Desert, over 5,000 meters above sea level, the air is so thin and dry it feels like another world. This extreme, arid environment is the perfect home for the Atacama Large Millimeter Submillimeter Array, or ALMA, the most powerful observatory ever built for seeing the cold, dusty universe. It does not look for light or heat, but for the faint radio whispers emitted by molecules and dust grains only a few tens of degrees above absolute zero. To capture these whispers, ALMA is a symphony of precision, an array of 66 high-tech antennas that can be moved across the desert floor like pieces on a cosmic chessboard. Spaced up to 16 kilometers apart, they work together as a single, gigantic interferometer, creating images of stunning clarity and detail. This is the instrument that finally pierced the veils of cosmic nurseries. For decades, astronomers knew stars and planets were born in dense clouds of gas and dust, but those clouds were opaque walls to visible light. ALMA vision changed that. It peered directly into these dark wombs, revealing protoplanetary disks in breathtaking detail. Around young stars, ALMA saw not just smooth rings of dust, but intricate structures, gaps, and spirals carved by newborn planets sweeping up material as they orbit. We are watching solar systems under construction, seeing the very processes that, 4.6 billion years ago, formed our own sun and planets. But ALMA gaze stretches far beyond our galactic neighborhood. Its sensitivity to cold gas allows it to look back to the era of the first galaxies, just a billion years after the Big Bang. It detects the faint glow of carbon monoxide and dust in these infant star systems, revealing how they grew by feasting on cold streams of primordial gas. ALMA showed that the earliest galaxies were not just chaotic blobs, but often possessed rotating disks of gas, orderly structures emerging surprisingly quickly in the young cosmos. It even studied the environment around supermassive black holes in distant galaxies, mapping the frenzied, swirling gas that feeds them. By tuning into the cold, molecular universe, ALMA completes a picture. It connects the dots between the diffused dust seen by Spitzer and the violent endpoints witnessed by Chandra and Fermi. It shows us the quiet, cold, and patient phase of cosmic construction, where gravity gently pulls together the dust and gas that will one day ignite into stars and coalesce into worlds. In the silent, thin air of the high desert, ALMA listens to the softest murmurs of creation, the slow, cold whisper that says, "Here, something new is about to begin." ALMA listens to the cold whispers of creation, but to hear the very first words of the cosmic story, we had to build an observatory that could see the heat of the beginning. The James Webb Space Telescope is not merely Hubble's successor, it is a machine designed to do something profoundly different, to look back to the cosmic dawn. To achieve this, it had to become an instrument of ice and shadow, stationed 1,000,000 miles from Earth at a gravitational balance point called Lagrange 2. Here, it could permanently hide behind a colossal, tennis court-sized sunshield, keeping its instruments in a perpetual, deep freeze colder than the void of space itself. This cold is essential because Webb is an infrared telescope. It sees the universe not in the visible light our eyes perceive, but in the longer wavelengths of heat. The most distant galaxies in the universe are fleeing from us at such incredible speeds that their light is stretched, or redshifted, out of the visible spectrum entirely and into the infrared. To see them, Webb's primary mirror had to be enormous, over 6.5 meters across, far too large to launch in one piece. The solution was a masterpiece of origami engineering, a mirror composed of 18 hexagonal segments of gold-coated beryllium that folded up inside the rocket and then unfolded with nanometric precision in space. This golden eye, chilled by its sunshield, is the most powerful time machine ever built. Almost immediately after its first images were released, it began rewriting cosmic history. It found galaxies that were not just ancient but mature, full of stars and complex structures, at a time when the universe was only a few 100 million years old. This was far earlier than most models had predicted, forcing astronomers to reconsider how quickly the first stars and galaxies could have assembled after the Big Bang. But Webb's vision is not only trained on the far past. It has turned its infrared gaze on the atmospheres of planets orbiting other stars, performing a kind of remote chemistry. By watching starlight filter through an exoplanet's atmosphere during a transit, Webb's spectrographs can detect the unique fingerprints of molecules. In one early study of a gas giant called WSP-39b, it made a landmark detection, clearly finding carbon dioxide in its skies. This was more than a discovery, it was a demonstration of a powerful new capability. For the first time, we have a tool that can systematically analyze the air on distant worlds, searching for the chemical imbalances that, on Earth, are signatures of life. Webb stands at the frontier, its golden segments collecting the faint, redshifted glow of infant galaxies while simultaneously decoding the atmospheres of alien worlds. It connects our deepest past to our most tantalizing future, asking two fundamental questions at once. How did it all begin, and are we alone in the story? The golden eye of James Webb peers into the deepest past, but the next great transformation will not look back. It will watch the sky in motion, high on Cerro Pachon in Chile, the Vera Rubin Observatory is being built not to stare but to scan. Its mission is audacious in its simplicity, to take a portrait of the entire visible southern sky, not once but every few nights for an entire decade. This relentless, automated patrol will be powered by the largest digital camera ever constructed for astronomy, a 3.2 gigapixel behemoth that captures an area of sky equivalent to 40 full moons in a single exposure. Night after night, this vast electronic eye will gather petabytes of data, compiling a time-lapse film of the cosmos on a scale never before attempted. This project is called the Legacy Survey of Space and Time, and it will turn the static universe into a dynamic, moving picture. The sheer volume of change it will record is staggering. It is expected to catalog over 20 billion galaxies and spot millions of previously unknown asteroids and icy objects in our own solar system, creating an unprecedented early warning system for objects that might pass near Earth. But its most profound discoveries will be of things it cannot directly see. By tracking the subtle distortions in the shapes of billions of distant galaxies, caused as their light passes through the gravitational fields of invisible mass, the survey will map the cosmic scaffolding of dark matter in exquisite detail, revealing the hidden skeleton of the universe. Even more ambitiously, by measuring how the distribution of galaxies and galaxy clusters has changed over cosmic time, the survey will place the most stringent constraints yet on dark energy, the mysterious force accelerating the expansion of the universe. The Vera Rubin Observatory will not answer these mysteries with a single brilliant image, but with a relentless accumulation of data, the statistical whisper of billions of points of light telling a story of invisible forces. It represents the future of discovery, where the universe is understood not through isolated glimpses, but through the patient observation of change itself, a 10-year-long cosmic movie where every frame holds a potential revolution. This entire journey reveals a pattern deeper than any single discovery. Each leap forward followed a recurring rhythm, a set of transformations that built upon the last like a cosmic ladder. The first and most obvious drive has always been for more light. From the naked eye at Stonehenge to the colossal metal mirror of the Leviathan, and onward to the segmented gold of James Webb, the quest has been to build a bigger eye, to gather more photons from the deepening dark. But aperture alone was not enough. The second great shift was learning to see in colors invisible to us. We moved from Galileo's visible light to the radio whispers caught by Jodrell Bank, the searing X-rays mapped by Chandra, the cold infrared glow revealed by Spitzer and Webb. Each new wavelength peeled back another layer of reality, showing us that the universe we see is only a narrow slice of a much richer symphony. The very nature of the observer changed just as radically. Astronomy began with individual genius, a Galileo pointing his spyglass in solitude. It evolved into the institutional might of the Paris and Yerkes observatories, then into the global collaborations of the VLA and LIGO, where discoveries are credited to collaborations of thousands. Today, projects like the Vera Rubin Observatory run on automated surveys, their discoveries mined from petabytes of public data by researchers worldwide. The lone stargazer has become a node in a planetary network. Perhaps the most profound transformation has been in our relationship with the cosmos itself. We began as passive witnesses charting the motions of distant lights. Then we became active probes. We bounced radio waves off planets with Arecibo, taking the measure of our solar system. We sent Hubble and its successors into exile beyond the atmosphere. And finally, with LIGO, we stopped merely looking and started listening, feeling the vibrations of space-time itself from collisions we could never see. We are no longer just an audience to the cosmic play, we are interacting with the stage. These patterns are not a random list of upgrades. They are the logical, cumulative steps of a single, grand endeavor. Each new tool solved the limitations of the last, and in doing so, revealed new and deeper questions. The mystery of the spiral nebulae, seen through Lord Ross's giant, demanded the distance measurements of Hubble's Hooker telescope. Hubble's expanding universe demanded the precise mapping of the Sloan survey to trace its large-scale structure. That structure, in turn, pointed to the dark matter and dark energy that observatories like Chandra and Rubin now hunt. Isolated puzzles have linked together into one coherent, if breathtakingly complex, narrative. Our cosmic story is still being written, its next chapters waiting for the next transformation. But look back at the arc, from stones aligned with the solstice sun to an observatory that feels the ripples from colliding black holes. It tells us something fundamental about our species. Our curiosity is a kind of engine, one that constantly redesigns its own tools to reach just a little further, to listen a little more closely, to turn the unknown not into a void, but into a story we are all part of telling. What will we build when the next question demands an eye larger than a planet, or an ear more sensitive than spacetime itself? The arc from that first stone circle to an ear listening for spacetime ripples is a map of human curiosity itself. Every time we built a better tool, the universe responded not with final answers, but with deeper, more beautiful questions. Our view of the cosmos is not something we found. It is something we forged piece by piece with glass and metal, with code and courage. The story of these 25 watchtowers is ultimately our story, a chronicle of how we learned to extend our senses beyond the limits of our bodies, to see with mirrors wider than cities, and to hear with antennas strung across continents. Each observatory was a question made physical, and the universe has never failed to reply with a revelation that reshaped our very place in the grand scheme. This transformative journey is far from over. Even now, new sentinels are rising. In the Chilean desert, the extremely large telescope is taking shape, its 39-meter primary mirror promising to directly image exoplanets and peer into the hearts of infant galaxies with unprecedented clarity. Plans are being drawn for space-based interferometers that will hunt for Earth-like worlds by blocking out the glare of their parent stars, and for gravitational-wave detectors in space that will listen for the mergers of supermassive black holes, events too low-pitched for any Earth-bound instrument to hear. These future observatories will not just add to our knowledge, they will inevitably force another great rewrite, challenging what we think we know about planetary formation, the first stars, and the nature of reality itself. The story continues with every new night of observation, every new dataset released to the world. So stay curious, follow the work of these cosmic watchtowers, old and new. Because the next great revelation, the one that will once again transform our view of everything, is already waiting in the dark for the next tool we build to bring it into the light.